Section 6.1 is integration by parts. It's our first section of the course. It's our first section of chapter 6. Chapter 6 is integration techniques. So if we're going to get very far at all with calculus, we're going to need to be able to integrate various functions and settle whatever different types of integrals we might come across. You've already seen in Calc 1 U substitution as one trick for integration. And probably in your Calculus 1 experience, you've also noticed that um, integration is not quite as easy as differentiation, even though they are inverse processes of each other. In other words, differentiation undoes integration and vice versa. We find that differentiating functions is always much easier than integrating them. So what we realized in Calculus 1 was that the U substitution was sort of the counterpart or the inverse of a chain rule. We would undo a chain rule derivative through a U substitution. And our next technique, integration by parts, which we're learning in this section, it's the opposite of a product rule. So if we have the product of two functions which don't look like the result of a chain rule, in other words, are not now available for U substitution, we might be able to use integration by parts. And the method is pretty simple. We start with the idea of a product rule, the derivative of a function u times v with respect to x. And we remember that the product rule is derivative of the first times the second plus the first times derivative of the second. And that's our product rule for differentiation. Now, if we shuffle terms around, namely we want to solve for this term, u times dv dx, or u times v prime maybe, and we end up with this expression after we subtract du dx times v of x from both sides. And now we take the antiderivative or the integral of both sides. We have this on the left. On the right, this term, the integral of the derivative is just whatever the two original functions were, whatever the function we were operating on, which in this case is the product of u and v. So the integral and the derivative cancel here, and then the last component is the integral of this. So in a way, it looks like we only trade where our integral sign is in this integration by parts formula, because this is ultimately the formula we're going to use. So we trade an arrangement of u times the derivative of v as our integrand for the derivative of u times the function v as our integrand. And it might seem like it won't help us very much, but depending on what u and v are, this could be a very powerful tool. Notice that on the right-hand side, this part of the formula no longer has an integral in it, so we've already arrived at a closed form for that portion of this integration. So that's essentially done. It's just whether or not this integral, when we're done applying this formula, is something that we can actually handle and solve. So a nice shorthand for this is given below in this formula right here. U dv is equal to, integral u dv is equal to u times v minus integral v du. And we'll write that at the top of the page probably several times as we go through problems. So as we have above here, that's exactly the case. I'm keeping a copy of it so we are reminded of what we're dealing with. Now we're asked to evaluate the integral of x cosine x dx. So right away, we'll realize from Calc 1 that this isn't a closed form integral. In other words, we don't just know an antiderivative off the top of our head that settles this. If there wasn't an x here, say that x was gone, and we just had the integral of cosine of x, we'd only be dealing with the antiderivative of cosine of x, which is pretty straightforward. As is, we have a product of two functions in the integrand. We might consider a u substitution, in which case we'd look at this function inside of cosine, and we consider what its derivative is. It's 1, which is not equal to that function, or at least not off by a constant factor. So a u substitution won't help us here either. So this is a good candidate for integration by parts. And in our situation, we have u dv in our integral. So here's u times dv in our integral. Now one of these could play the role of u, one of these could play the role of dv, or v prime, however you want to see it. It turns out, in this case, if we choose u to be equal to x and dv to be equal to cosine of x, then taking the derivative with respect to x, here we end up with du is equal to 1 dx, right? Some of the details that are happening in this are actually du dx is equal to 1, and then we solve for du so that it's 1 times dx. Right? So du is equal to dx, and that's what we have here. Now dv is cosine of x, and we could, technically there is a dx right here. We take the integral with respect to x of both sides. We arrive at v, canceling out the differential on the left, and the antiderivative of cosine of x is sine of x. So v is equal to sine of x. So we're still not sure whether or not this is going to work. You're not really sure until you plug all of these values into our formula. So we go back up here to follow this structure, this template. It's u times v. So it's this function times this function, and that's outside of the integral. And that gives us x times sine of x. And then it's minus the integral of v du. And that is sine of x times, well, du is just dx. So we have sine of x dx. Okay, once we arrive at this right-hand side from integration by parts, we typically want to look at the integral and say, is this something that I can integrate by another known method? Is it something I could possibly use integration by parts on again? That might help. But when we look at this one, we realize it's just the antiderivative of sine of x, and that's going to be negative cosine of x, as we see down below. So a negative negative leaves us with a positive cosine of x. And notice that all along the way, x sine of x is already done for, and that's part of our antiderivative in our final answer. So the indefinite integral of x cosine of x is equal to this function right here. And that's thanks to integration by parts. Don't forget that constant plus c of integration. Now, next up, another example, and we'll do several before we're done with this section. We have the integral of natural log of x. So a nice way to come up with what this antiderivative is through the following. We write down integral natural log of x dx, and really it's curious how we might start this one. We have to remember that there is a multiple, a function multiple in front of this natural log, and that's 1 times that natural log. So there's our product that we might need. And in this case, we decide to let dv be that function, 1. So dv is that 1 that's times natural log of x. We let u be equal to the natural log of x, and we can proceed from here. So if we know that u is natural log of x, we'll want to know du. So we take the derivative of natural log of x to get 1 over x dx, or at least have it in terms of differentials as we have here. dv is 1, we integrate both sides to have that v is equal to x, integrating with respect to x there. So now we use our integration by parts formula. U times v is x times natural log of x minus the integral of v du, x times 1 over x. And, well, this should look pretty clear that it's going to work out in our favor. X times 1 over x is just equal to 1. So there's technically a 1 in this integrand, but that's the simplest integral we can deal with. The integral of 1 with respect to x is just x, as we see below. And on the left, we've got x natural log of x that came out thanks to our integration by parts formula. So these things all added together, or taking the difference of, is x natural log of x minus x plus c. So there's our antiderivative for natural log of x. Now, the nice thing about finding integrals or antiderivatives is if we take the derivative of this function, we should get natural log of x back. And I'll let the reader chase down the details on that one. That is exactly the case. So moving on, more complicated functions, step by step. We've got the integral 10x squared natural log of x dx. So first thing I'll do is I'll factor the 10 out of that integrand just to clean things up a bit. 10 sits out front times the integral of x squared natural log of x. We saw last time it made sense to let u be equal to natural log of x. These aren't fixed decisions. And when you learn this stuff, you might try the wrong combination first. But notice that if you were to choose dv to be equal to natural log of x, then you would have to integrate the natural log of x, and that might be kind of messy. In the previous case, if you'd have done that, you'd end up having to integrate the natural log of x, well, and that was the entire problem altogether anyway. So integration by parts would not help in that case. It's okay to make mistakes. It's okay to write this down, start out with one choice and realize it's just not quite going to work. So you'll have to reverse it and try the other choice or some other choice. Okay, there are some rules of thumb, but nothing is a sure shot. And you've always got to be a little bit dynamic in these. Anyway, we've chosen u to be natural log of x. The derivative of that is 1 over x. And the differentials are du equals 1 over x dx. Now dv is x squared. And integrating both sides, we get v is equal to, well, the power rule tells us 1/3 x cubed is the antiderivative of x squared. Okay, so plug that into the formula. It's u times v minus the integral of v du. So here is v du. And if this integral over here, again, it becomes something simple that we can handle, then this is a good choice. If not, then we have to change our choices. Maybe even try another method ultimately. All of that is times 10 off to the right. So we're not forgetting our factor of 10 in the problem. Now, moving down to where we start to work on this, we realize that, this function is just going to hold steady as the product of u and v. No more to do with that. And it turns out we factor a 1/3 out of this integrand. And x cubed times 1 over x is x squared. So we're really just integrating x squared with respect to x in this line. And that's something we can handle. So this looks like it was a good integration by parts move. Now we end up with all of this is the same. And our integral of x squared is 1/3 x cubed times the 1/3 that was already there with a minus sign in front of all of it. It's a good time to add a plus c since all the integral signs have disappeared. It's kind of a decent rule of thumb to use there. And we end up with 10 times each of these terms. We have 10 over 3 x cubed natural log x minus 10/9 x cubed plus c. And that finishes that problem. Okay, again, you might take a problem like this and make the wrong choices and have to flip around u and dv and try different roles for each of these variables and each of these functions. And there are more ways we can split things. We could have split this as this could have just been x and this could have been x times natural log of x. Whether or not that would have led us to an answer or been useful or easy to calculate is a matter of whether or not it would have been the right or decent choice to make. It takes practice and you're going to have to get some experience picking up these problems and making wrong choices first until you finally find a decent algorithm for yourself to make correct choices, or at least a good sense of how to make good choices in these problems. Next up, e to the x cosine of x. Find the antiderivative of this function. So this one, it turns out, and it's usually a good idea anytime we deal with integration by parts, to give our integral a name or a handle. We'll call it I. That's a very common thing to do for these integrals. So we'll let I be equal to the integral of e to the x cosine of x. And the reason we do that will be apparent a little bit later on. So let's run one round of integration by parts. I'm going to choose u to be cosine of x, and I'll choose dv to be e to the x. And honestly, a major part of my motivation for this is because I don't want to have to integrate sine and cosine because there's a plus or minus sign that shows up. It can get kind of confusing when we're taking derivatives and antiderivatives. E to the x is a very easy function to integrate and differentiate. So I'll choose to integrate e anytime I get that opportunity. Now, whether or not it works in the problem is just a matter of that problem. So for now, I'm just choosing this one. Hopefully things work out well. So if u is cosine x, du, the derivative of cosine x, is negative sine x with dx for the differential there. And v is equal to e to the x. It's the antiderivative of dv, which is e to the x. So that's nice and simple. We plug this in, we have u times v in different order. That's v times u in this order, e to the x cosine x. And then minus the integral of v du. So here's v, here's v, and here's du. So it's negative e to the x sine x for v du. Now we have two minus signs, so those will go away. We have a plus sign here. And it's the integral of e to the x sine of x dx. Well, it didn't seem like it got us very far down the road. We know from probably any bit of intuition that e to the x and sine or cosine are never going to leave this integral. So we're going to have to look for something else. So let's keep an eye out for it as we progress. But let's try integration by parts one more time. Let's just push it a little further and see where we end up. So this time we'll use a similar format, except we're looking at this integral, and we'll let u be the trig function, sine of x, and dv be e to the x again. The derivative of sine x is cosine x. The antiderivative of dv e to the x is v equals e to the x. Okay, so again, we chose e to the x on the derivative side because it's easier to integrate that one. So when we do that, within this piece, we've got an integration by parts. We've got one term added to an integral. So here's our first term here, and then plus our new u times v here. And then we've got minus the integral of v du. And this is the integral of v du, e to the x cosine x dx. Okay, so that's a good thing. We might look at it and say we've gotten nowhere really. We've gotten all the way back to where we started in terms of an integral. But the good thing about this situation is this is I. This is equal to the integral that we started with. If we remember that there's an equality at work here, we're trying to find this integral e to the x cosine x dx, we can treat it as an algebraic term. And we've already given it the name I, so that'll simplify that. So really at the end here, what we have is this is a minus I after these two expressions added together, these two functions added together. So if we add I to both sides, we'll get it away from the right-hand side. And we see it over here, added plus I to both sides. It's canceled on the right. And we now have 2I is equal to these functions here. And to solve for I, to find our integral on its own, we just divide by 2. So this comes out to 1/2 e to the x. And then we've factored out e to the x away from cosine x and sine of x. That's neither here nor there. You can do that or not. I think either answer is acceptable in WebAssign, and certainly anything boxed in any of these lecture slides is always acceptable on a quiz or test. So there it is. We were able to detect, we ran integration by parts twice. Then we saw our original integral show up, and we didn't quit on the problem. We said we can bring this back around and connect it to where we start, because it's actually equal to this. We just factor it over, add it to both sides, combine it, and then we solve for that algebraic term as if it was just a variable I. And we end up with exactly what we're looking for. And again, a nice thing about this integration by parts or any integration problem is that we can check this answer by taking its derivative to make sure we get back e to the x cosine of x when we're done. The reader is certainly encouraged to do so. So moving along, of course, this tool can help us build other tools. And the most immediate tool that we can build with the integration by parts formula are reduction formulas. So our first reduction formula looks like the following. We have x to the n, e to the x, integral of that. And we've got a formula, so it seems, that this is equal to x to the n, e to the x, minus n times the integral of x to the n minus 1, e to the x. Now, the reason this is called a reduction formula is because it takes the exponent of n, which is a positive integer, by the way, and it reduces it by 1 as we move to the right in the formula. Now, if x was equal to 1, or if n was equal to 1, then x to the 1 minus 1 would be x to the 0. That would be just a 1 times e to the x. It would be the integral of e to the x, and we'd be able to resolve this integral on the right, and we'd be done. If it wasn't, well, we stepped it down to some other positive integer. And we could again step that one down through another application, and then another application until we finally get to x to the 0, where we can integrate e to the x. Okay, so we can use this reduction formula over and over, and that's more or less why it's given that name. Now, before we use it, let's derive it. Let's see where it would actually come from. So we'll start, just like proving an identity back in a trigonometry course, we start with the left-hand side. We write that down. And then we want to arrive at the right-hand side. Well, it turns out this one's pretty straightforward. With integration by parts, we let u be x to the n and e to the x be dv. And we're kind of motivated by that because we know that on the right, x to the n becomes x to the n minus 1 in the integral. It probably happens by a derivative. And we see that here, n times x to the n minus 1. Integrate dv equals e to the x to get v equals e to the x. And now all the parts more or less fall in line. We can take u times v here and here to get this term. And that's resolved. It's no longer in an integral anymore. Minus v du, this times this in the integral. We've already factored the n out of the integral because it is a constant with respect to x. And we end up with x to the n minus 1 times e to the x dx. So that's our reduction formula in this case. We've proven that this formula actually does hold thanks to integration by parts. It works out. We won't always prove reduction formulas. We might have some around that we just use, but the way to prove them is typically in this format. Now, next, we've got, let's apply it, or let's apply something like it. We've got an integral of x squared e to the x. We'd like to evaluate this integral. And well, instead, it asks us to use the reduction formula above, and the work I have is actually using integration by parts twice. And either way is just fine. I prefer to use the basic tool I know over silly formulas and things like that I have to remember, but that's just a matter of taste. So in our first round of integration by parts, we've got x squared e to the x. So u will be x squared, dv will be e to the x, and du is 2x, v is e to the x. Okay, put that together in our integration by parts formula, and let's see what happens. Our integral becomes u times v, then minus v times du, and that's actually v times du in this integral. Just they're a little bit out of order, which is no big deal. We can factor that 2 out, and this term again is taken care of. No more to worry about in terms of it. Hopefully we can get this integral into something we can manage. I don't know this integral yet, and immediately off the top of my head like an antiderivative, but it does look like I could use integration by parts on it once again, and that's exactly what we'll do down below. We'll go over here. U now is equal to x, or it looks like we kept the 2 with it this time. Remember, constants we have some liberty with constants. We could just leave it out front, or we could bring it into this integration by parts step. That's fine. And we let dv be e to the x, and du is equal to 2 dx, and v is equal to e to the x. That being the case, we have u times v, and that fits in nicely on the other side of this minus sign. So here's u times v, and then minus the integral of v du. So there's v, and du was 2. So now we have, it's just going to ultimately be the integral of e to the x with a factor of 2 times it. And that's something we can resolve. The integral of e to the x is just e to the x. And we see that happen down here. Before we get there, we have to realize that here's this term, and we've got some minus signs and constants to take care of. There is a minus in front of this, so it becomes negative 2x e to the x, and then a minus minus becomes a plus 2e to the x. And since all the integral signs are now gone, it's a good time to add plus c. That's a rule of thumb. If you go by that, you really won't get in trouble at all in this class. In terms of those constants of integration. Once the integral sign's gone, add a plus c, and that's a nice time to do so. And that's for indefinite integrals, of course. Okay, a few more examples to go. One is the suggestion at doing this problem. Use integration by parts to derive this reduction formula. It'll be a very simple method, or very similar method to what we did before. You will use this side to have a look over here and say, okay, I need to make a choice for u and dv. Now I would pay close attention to what happens to the powers of cosine to the n of x. Looks like it's stepping down in some form or another. So maybe, and particularly right here, maybe that tells us what u or v might be. So this has got to be u, or it's going to be v. And I'll just leave that in place as a hint for the reader. But that's addressing the first hint that I've got below. So that one's been talked about. And then we'll, it's not a bad idea to give this integral a handle, call it I, and this will be kind of similar to what we saw in a previous problem. Look for I to show up after you apply integration by parts again. Combine those two i's, deal with any constant factors they have, and then solve for I to get hopefully the formula that's on the right-hand side. This is a sort of above and beyond exercise. Maybe come back to it after you've done several problems from WebAssign or several problems in the homework and out of the textbook. If you feel like you can do it right now, by all means, give it a shot. But this is a pretty high-level problem to deal with at the moment. Okay, to get back to some more explicit problems, though, just solving things, not necessarily deriving formulas. They ask us to use the previous reduction formula or integration by parts to evaluate this. So you might try the formula out on this. I'm using integration by parts in the notes I have here. Either way is just fine. So let's give it a rip. We've got cosine cubed of x. It seems like it's one term. So if we suspect we can use integration by parts, remember we can take factors of cosine away from cosine cubed of x. Cosine of x times cosine squared of x is cosine cubed of x after all. So we've just peeled off one factor out of cosine cubed to have these two. And well, now we'd have to play around. We'd try u equals cosine squared x, or maybe dv equals cosine squared x. Notice that if you chose dv to be cosine squared x, things could get a little hairy. So there's a good question. What is the antiderivative of cosine squared of x? We don't know that yet. And we'll have to see that in section 6.2. So it turns out that wouldn't be a great choice. But as we've chosen it now, we can at least get started. So if u is cosine squared x, we're going to take its derivative. And the power rule says it's 2 cosine x. But cosine, the square is an outer function. So this is the chain rule being applied next. We get 2 cosine x times the derivative of cosine x, right? And what I would like to do, just to keep us all in mind of this, is that this is the derivative of cosine x. And that's coming from the chain rule, okay? Because that square is the outer function. The inner function is cosine x. So there's our reminder for that. It's hard to remember all the Calc 1 we need to recall as we go through this Calc 2 material. So dv is cosine of x. The antiderivative of cosine x is sine of x, so there's v. And let's put this together in the integration by parts formula. Integral of u dv is equal to u times v minus v du. Here is u times v, and then minus v du. So let's see. When we simplify all of this, it's got a minus sign in it. It's got a minus 2. So we have a minus negative 2 times our integral. So we end up with a plus 2 times our integral. And next up, it's v du inside. So there's our v times, well, the rest of this is cosine x sine x. So this is actually cosine x, to write it all in up above it, cosine x sine x times sine x for u and for v. And I'll leave that there so that we have it to refer to later. So that gives us overall cosine sine squared of x. Now what's happening in here that's a little bit confusing is we're starting to look at a u substitution to continue to solve this integral. This should have happened on another line. The notes aren't as clean as I'd like them, but we can deal with it. Now we're facing this integral, and we want to look at it and say, okay, integration by parts, because it's a product, maybe that's possible, maybe it helps us, but let's pause and try to think about the tools we already have. Is it a straightforward antiderivative? No, cosine x sine squared of x, we don't know an antiderivative for it right out of the gate. But what we do recognize is that sine of x is the inner function of sine of x quantity squared. And we know that sine of x's derivative is cosine of x. So we've got a perfect u substitution sitting in front of us. And the parts are this. U is equal to sine of x, so we have u squared here. And then du is cosine of x dx, and that's exactly what's being pointed out in the red text that was already there. Okay, so that being the case, we are able to rewrite that integral as 2 times the integral u squared du. And of course, that's plus the term that came out by integration by parts already. And we just need to handle this u integral. And that turns out to be 2/3 u cubed by a power rule, which is nice and simple. And then we undo our u substitution. Remember that u is sine of x. So then we'll have 2/3 times sine of x cubed. And that's this term right here. Okay. In between, we wrote down the details of our u substitution. And that, again, was, more or less highlighted up here, broken apart in these steps. Maybe I got a little overzealous with adding the notation. It's harder to see it after the fact than while it happened. But at any rate, an integration by parts and then a u substitution for the subsequent integral gets us to where we are here. And also note that you could use the reduction formula as well. And I'd recommend students try that also, just to see that that reduction formula will work. So one final problem involves a definite integral. And again, remember, a definite integral has limits of integration. So we should get a number out of this. It might be a transcendental number or an irrational number with e or pi or something in it, but we should get a number and no longer a function. So we've got the integral from 0 to 1 of negative 2x e to the 4x. Okay, first things first, let's factor negative 2 out of the integral to the front, just to clean things up a little bit and make stuff more manageable while we work on the integral itself. Now, my first step would be to say, I want to integrate this. Let's use dv as the exponential function. Again, when life is good and things work out this way, this is always a nice pattern. It won't always be the case that you can choose dv to be the exponential function. So keep an eye out for those exceptions. U will be x, and that's nice too because the derivative of x is 1, so we just have du equals dx. And then e to the 4x is the antiderivative of that is 1/4 e to the 4x. So e's antiderivative is itself, and then the u substitution that happens there gives us that 1/4 that comes out. So the details of this are down here. To get from here to here, just remember that there's technically a u substitution happening. One nice way to do it is to say, well, e's antiderivative is itself. It needs some kind of constant. If I were to take the derivative of this function here, I'd get a 4 out, but I need it to be e to the 4x. So I'll put a 1/4 so that 4 cancels. Maybe you see that. If not, have a look below. Okay, so with these pieces in place, we have u times v is x times 1/4 e to the 4x, and that's this term right here. And now the new thing that happens is we're going to evaluate at our endpoints from 0 to 1. This is closed up. There's no more integral to do there. So we can evaluate that function from 0 to 1. Maybe we don't get in a hurry about it, but we can always take care of it because this function might blend with, might combine with what happens later. And then we have minus v du. Well, minus v du is this function times this one. That's nice. 1/4 e to the 4x dx leaves us with this. And that's a function we can handle. We'll factor 1/4 out. We'll take the integral of e to the 4x and realize that we've already done some of that work down here. And of course, that constant factor of negative 2 that was in front of the integral, we're just keeping it along. It's outside on the right. Either side is fine. But as long as we keep track of it for the end of the problem. And going through these steps, we apply our limits of integration. Remember, this is the function evaluated at 1 minus this function evaluated at 0 here. So evaluation at 1 minus evaluation at 0. In other words, plugging in the number to the function for each of those and subtracting, top minus bottom. And then this is our integral that we need to resolve here. Well, again, we know what that integral is with a factor of 1/4 in front of it. Gives us this term. These are the details of what's going on over here. So we're going to have a 1/16 e to the 4x evaluated from 0 to 1. And that's what this looks like. E to the 4 times 1, e to the 4 times 0 is e to the 4th minus e to the 0th. And our constant became negative 1/16 from this multiple. And we see that we've got negative 2 times all of this. We don't want to forget that multiple in the very end. It's a good thing we brought it along the whole time. And Of course, I could combine this a little bit better, but what we see is that -2 hit -1/16 and gave us a +1/8. And then -2 times +1/4 gave us -1/2. Of course, there are 2 e to the fourths here. This could be simplified a little further. Again, like I said, I'm not very picky about these closed forms when they're written. So you just have to pay attention in WebAssign. So maybe this is -1/2 plus 1/8 is, what is that, -3/8, I believe. So we could write it as -3/8 e to the fourth minus, looks like 1/8. So that might be a good way to write that as well. This is just an alternate form. So that's it. There are lots of these problems to do. And I should point out at the very beginning of these notes, you'll see these book problems / test bank problems. You're responsible for all of these by the time you get to the test that includes this section, and that'll be the case for every section to follow this one. Be sure you can do all of those book problems. Keep a notebook of them. Keep a notebook of the examples even. It's nice to start with the examples and mimic them. Try to get the same answers without referring to them after you've looked at them a little bit. And then move on to the exercises, and then move on to the WebAssign homework. And maybe you kind of spiral through. You do a little bit of each every time you sit down and work on these problems until you're done with all the WebAssign problems and the book problems. So that's integration by parts. Next, we'll do trigonometric integrals and trigonometric substitution in 6.2. And I hope to see you there.